The most powerful laser in the world is now up and running on the outskirts of Prague. The HiLASE Laser Centre is the result of Czech-British cooperation helped with European funds. It's hoped that many of the applications that will be tested there will have an almost immediate impact in certain fields such as aeronautics, medicine and the car industry. Others could contribute to scientific advances further down the line. It's also hoped that the laser will put the Czech Research Centre on the map as a leading institution in a sector where the US, France and Japan are also very active. We spoke to one of the laser research team leaders responsible for both industrial and scientific advances, Antonio Lucianetti. He explained, first of all, where the name of the laser came from.
The name of the laser is actually Bivoj, and according to the Czech legend, Bivoj was so strong that he could catch a wild boar with his bare hands. In physics, however, we measure the power in the unit of watt or watts. So 1 kilowatt is 1,000 watts. How can we generate such big average power? The architecture of our laser is relatively simple. You have a low energy pulse at the beginning, which is generated in a so-called oscillator. And this pulse is amplified in a series of laser amplifiers with larger and larger apertures. There is a fiber-based front end, a so-called regenerative amplifier, a booster amplifier, and finally two cryogenically cooled multi-slab amplifiers. And at the end, the output parameters are 100 joules and 10 hertz, which makes exactly 1 kilowatt. An interesting feature is the pulse duration. For those who are not familiar with pulse durations in laser physics, as you know, the second is the unit of time, but these sophisticated machines can generate a fraction of seconds. So we are speaking about nanoseconds. And a nanosecond means 1 billionth of a second, so extremely short pulses. So this is a brief description of the laser.
Okay, and focusing just on the one kilowatt, for how long had people been trying to get this sort of power into a laser? And if I could be more exact, maybe, I think the important thing with your laser is that it's sort of like continuous. It's not one burst of sort of laser power, as it were, but it's a continuous stream. Is that correct?
Yes, it's correct. Actually, this stream is a measure in frequency, and as a unit we are using the hertz. So actually we have a maximum of 10 hertz, means 10 pulses in a second. This is relatively easy to achieve with ordinary technology. The main result here was the average power, so-called average power, which is a combination, or it's actually the product of the energy and repetition rate. So to achieve high average powers, you need higher and higher energies and higher repetition rate. So just to give some numbers, the previous record was 60 joules, and it was achieved at the Lawrence Livermore National Lab in the Bay Area near San Francisco. And actually I was working as a postdoc there, so I remember the excitement. And this value of 60 joules remained for about 10 years. And finally, we were able to achieve 100 joules with this strategic partnership with the British laboratory. So it's really a world record, and now we have a lot of feedback from the community, scientific community, because there are also very interesting applications you can do with these 100 joules at 10 hertz and nanosecond pulses.
I mean, how will that affect research going forward, and how might that affect the world we live in?
Yes, so there are two kinds of applications, industrial applications and scientific applications. So let's start from the industrial applications, because this is what our institute and our research center is mostly doing at the moment. So an interesting industrial application is the so-called laser shock peening, and I will briefly explain. If you consider the surface of a metal, just an ordinary metal like copper, iron or steel, the surface is never perfect. It's never flat, completely flat. And if you have a zoom or a microscope to look very carefully on the surface, you will see that there are some micro cracks, means small cracks. And thanks to the LSP, these micro cracks will be somehow removed, or by the way, LSP is a surface treatment by which a laser pulse is employed to strengthen engineered materials. And this is interesting in aeronautical industry for applications like gears, turbines, or fan blades. And Boeing and Airbus are very interested in this process. And I was reading recently that in the next 2 decades, more than 30,000 new airplanes with LSP-treated engines will fly. So we will probably fly on one of those planes in the next 20 years, I'm pretty sure. So aeronautical industry.
I can imagine also in the nuclear industry, this might be quite interesting because of the recurrent problems with some of the quality of metal in reactors, and if you can have better quality metal in reactors, then this would certainly solve a few headaches around at the moment. But,
Yes, you're right. And actually in Japan, this technique, this laser shock peening, was used exactly for the nuclear industry. It is a very special environment. You know, you have these metals in a very special radioactive environment. So these micro cracks can have a very bad effect on the whole power plant. So this technique is also very interesting for nuclear industry. And actually we are planning to have also some collaboration with the local, as you know, nuclear industry, because they have also some nuclear power plants here in Czech Republic. Another interesting industrial application is the cutting or drilling of materials for automotive and aerospace industry. And we have also already done some work for the local industry.
Could I just stop you there? I mean, presumably, is it you can cut much more exactly, or I mean, I presume it's a question of the exactness or the detail of the cut, or is it the fact that you can do it a lot quicker, or what is the advantage?
Yes, actually both. You should think that a laser is a very precise tool, because when you focus the beam to a small spot, you can have something like 50 or 100 microns, which is 1/10 of a millimeter. So you have a very sharp and precise knife to cut and also to drill holes. So you can do very small holes of the order of, say, 100 microns or 200 microns. And this is very interesting for a number of applications in automotive, also in aerospace industry. So this is a very precise tool, and there is no mechanical tool that can do these things with the same precision and accuracy. Another area where we think our lasers will be used in the next 10 years is a so-called laser-induced damage threshold. As you know, we are using optics, so optical elements, lenses, mirrors, and so on, and these optical elements are damaged. So and just to give an example, in our case, 30% of the cost of the facility is on optical components. So it's important to understand how this is happening, why, and so on. So this is something unique that we can do only in our facility. And last but not the least, medical applications. As you know, this is a very important area. Because society needs also doctors and hospitals. And we can also contribute in this area because with this laser shock peening, you can increase the resistance of orthopedic implants, for example. As you know, if you have an accident or you have something like that, you have to put some implants. And these are made of metals, special metals. So laser shock peening will increase also the resistance of these orthopedic implants. So this is another interesting area, I think, for the industrial applications. Then we have scientific applications. I'm a researcher, so I'm also interested in scientific applications. Medical engineering, I would call it. With these lasers, which are generating nanosecond pulses, which is relatively long for laser people, Actually, we can use our laser to pump another laser, which will generate shorter pulses. We are talking about picoseconds, so even shorter. And if these pulses are focused on a target, on a gas target, for example, they can generate high-energy protons. And these protons can be used for a new class of oncology or tumors treatment. As you know, that this is a big problem for many people, so we can also contribute in this area of medical, in the medical field. Another interesting scientific application is the generation of X-ray sources. Again, when you have a laser beam, you can focus on a target, then you can generate X-ray sources with high energy. And these X-rays can be used for advanced imaging, for inspection and security in airports. And this is another critical issue. As you know, we are all traveling more and more in airports, and security is one of the biggest issues for not only for Europe but for the rest of the world. So this is also another interesting scientific application for the next, let's say, 10 years.
Mm-hmm. Okay. And maybe just to go to the background, why is it that the Czechs and the British have sort of teamed up on this? How did that partnership evolve?
The main reason, when we received the money, the funding from the Czech government, we had only 3 years to build this laser with a top performance. And so the easiest way was to subcontract the construction of this laser to a well-known British laboratory called STFC. It's actually located near Oxford. And during the construction, we had several discussions on various technical issues, and we also sent people from the Czech Republic to UK, and it was really successful. So this strategy has turned out to be successful because at the end of the project, we were both happy. And we proposed to the British colleagues to apply for a joint grant to the European Union. And finally, we got 45 million euros from the EU and the Czech government. So now we are in the phase of upgrading our research center to a center of excellence. So teaming up with the British team was really a good idea, and we hope that for the next six or even more years we will continue to be at the front of the laser technology together. Okay.
And after that, I mean, it's basically a research partnership, or I mean, is there any likelihood some of the aspects might be spun off into commercial businesses or anything like that?
This is a so-called technology transfer. So this is one area where, again, we could learn from the British because they have a lot of experience in this area. So we will work with them, learning the best practices. Yeah, we will start soon to make our lasers available to the external world, because our goal is to serve a broadly based scientific and industrial user community. And so doing this, we hope there will be new ideas for also spin-off companies or patents and so on. So definitely technology transfer is one of the main, or one of the key issues for the next, let's say, 6-10 years of the center, of the research center.